amplitude and how the A value in the equation, remember here's the equation of a sine or a cosine, the A value helped us determine the amplitude. Okay, now we're going to be looking at what the B value in the equation in a sinusoidal function does. Okay, so we need to know this term period. Okay, the period of the function is how many degrees or radians are in the function from one point to a point where it starts repeating itself. Okay, so in this model, in this picture here, it shows this point in red, okay, and then you go through and then you get back to that same point and then it starts repeating the same pattern again. So the distance between those 2 points, that's the period. That's one cycle, and the width of that cycle is the period. Okay, and it's going to be in like degrees or radians. So amplitude was half the height, and period is the width of a cycle. Okay, now it has this random point selected to show, but you can measure the period anywhere. The most common, or I don't know if the most common, but the easiest is probably from low point to the next low point. You can measure the period, or from high point to the next high point. That's also the period. Okay, so all of those are the same length. They're the same number of degrees or radians between them. So it doesn't matter where on the graph you measure. If there's multiple cycles shown, you just pick a single cycle. It can be a cosine cycle or a sine cycle. It doesn't matter. Okay, so from any point to a point where the graph starts repeating itself. Okay, that number of degrees or radians there is the period. Okay, the B value in the equation is used to help us determine the period. Remember the parent functions for sine or cosine that we graphed a couple days ago, the period, one cycle, we graphed from 0 to 360 or 2 pi. So one cycle of the parent function for sine and cosine was 2 pi. That's why to get the period of a transformed function, you do 2 pi divided by the absolute value of b. B is this coefficient inside the function, the coefficient of x or theta. Okay, so that's what your period, that's what it means when it says period, and this is how to find the period of the graph. So good on that? All right, so let's try this example. Okay, so first off, let's review what we talked about yesterday. What would the A value be here? Not 2, 1. Okay, look here at the equation again. Remember, A is the coefficient in front of sine or cosine. Okay, there is nothing in front of the sine or cosine here. That does not mean it's 0. If it was 0, 0 times anything would be 0. This wouldn't exist. Okay, it's an understood 1. Okay, so A is 1, which means the amplitude of the graph will be what? 1, because the amplitude is the absolute value of A. Okay, that's what we talked about yesterday. So now we're adding in period. Okay, what is the B value here? The 2. Okay, 2 is the coefficient of the x. Okay, so the period then is found by doing 2 pi divided by the absolute value of B, which is 2. What happens to those 2's? Yeah, 2 over 2 is just 1. Those reduce. So that's just pi. So the period of the graph should be pi, and the amplitude should be 1. Once we get this graphed, we're going to come back and check and make sure that that's what we graphed. Okay, it's a way for us to check ourselves. All right, we said when we're creating our table of values, we always start with the critical points column, and that we title or header that column with what we're taking sine or cosine of. In this equation, what are we taking cosine of? Cosine of 2x, okay? It is not just x, it is 2x. So yesterday, we didn't have any with a b value. They were all understood 1, so it was always just x. Okay, so now the b value being something other than 1, okay, is going to have a little extra step for us to do when creating our tables. Because now our critical point column is not our x column. Okay, so notice there's a column here to the left. Okay, so we're going to come back to that in just a sec. Okay, but we said yesterday to the right of the critical point column is always your trig column. Okay, this time we are doing cosine. It is not just cosine of x, this is cosine of whatever is in this column, so 2x. Okay, now remember, when we fill this column out, this is coming from, let me pull it up in the notes here, get back to it to refresh your memory. Let's see, let me find the right page, right here. When we talked about how sine starts at the origin, goes up, back down to the low, back to the x-axis. So sine at the critical points was 0, 1, 0, negative 1, 0. And cosine starts up at the high, goes through the x-axis down to its low, back through the x-axis to its high. So it's 1, 0, negative 1, 0, 1. So these are the numbers we're filling in the trig column right there. Okay, so the cosine of 2x column is going to be the 1, 0, negative 1, 0, 1. When you have your critical points and your trig column, those are the ordered pairs of the parent function. Okay, so I'm going to go ahead and plot those points. Okay, so 0, 1, pi halves 0, pi negative 1, 3 pi halves 0, 2 pi 1. Okay, and then I'm going to sketch that curve. Not the best curve. I'm going to try that again. Okay. Connect those, try and make it a little smoother. Rounded. A little better. All right, so that's the parent function. That's one cycle of cosine. Okay, now there is no amplitude change. It's an amplitude of 1, which is the same as the parent function, which multiplying by 1 doesn't change anything, does it? No, so we don't need a column to the right of the trig column to multiply in the amplitude. Okay, it's not necessary. Cosine of 2x, that is the entire function. So that is going to be the y value. That's the y column. Okay, but we don't have x alone yet, which we need to get. So we are going to have to work backward to get x by itself. Okay, so how do you think you're going to get rid of that 2 to get x by itself? You're going to divide it out. So anytime there is a b value in the function there, you're going to go backward from the critical point column to get x, to get rid of the b by dividing by b. Okay, so you divide out the b. Okay, so what that looks like here, we're dividing by 2. Now, some of you may need a little refresher on dividing fractions. Hopefully not on dividing 0. What's 0 divided by anything? Okay, but some people may need a refresher on this. If I have pi halves and I'm dividing by 2, when you have fractions in fractions, remember you take the denominator and you flip and multiply. So instead of dividing by 2, I'm going to multiply by, 1/2. You got to flip it. 2 flipped is 1/2. You multiply by the reciprocal. So that is pi fourths. You multiply straight across the top and the bottom. So half of a half is a fourth, right? Does that make sense? So this is pi fourths. Okay, pi divided by 2 is just pi halves. Okay, it would do the same thing here. What you end up doing when you're dividing by 2, you're just multiplying the denominator by 2. So that's going to be 3 pi fourths. Okay, and 2 pi divided by 2, what's going to happen? That's just going to be pi. Good. Now, the next thing I'm going to do is not technically necessary, but it's a good way for you to check that you've done that math correctly, because that's a really actually common place to make a mistake is dividing with fractions. Some people mess up and get the wrong values there. So one way you can check that you've done that correctly is to get a common denominator for these values. And then you can check that all of the points are evenly distributed. Okay, so if I wanted to create a common denominator between all of these numbers, it would be fourths. Okay, so I could rewrite this as 0 pi fourths. This is already 1 pi fourth. Okay, to change this to a fourth, I'd have to multiply it by 2. So I have to multiply the numerator by 2. So 2 pi fourths. Okay, this is already a fourth. It's 3 pi fourths. And right now this is an understood 1 for the denominator, so multiplying by 4. So 4 pi fourths. So when you have a common denominator, you can just look at the numerator to see the distribution. This is 0 pi, 1 pi, 2 pi, 3 pi, 4 pi. Isn't that evenly distributed? Okay, it's equidistant between each of those values. That's a good thing. That's what you want. Okay, so you don't have to get the common denominator, but sometimes it's helpful for you to check that it's evenly distributed. And if you are having to graph this by hand, like the graph is not already scaled, this gives you a nice thing to scale by to plot your point. Okay, now this graph is already scaled by halves. Okay, so fourths are going to be in between, right? So this is 1 pi fourth. So our points are 0, 1, pi fourths, 0, pi halves, -1, 3 pi fourths, 0, and pi 1. Okay, so I sketch the curve. Now I want to verify what I said at the beginning about the amplitude and the period. So the amplitude is from the high point to the midline, or you could measure from the low point to the midline. What is that distance? 1. Is that what we said the amplitude should come out to be? Yeah, so that checks out. That's good. Okay, and the period is from the beginning of a cycle to the end of a cycle. Okay, in this case, high point to high point. Okay, that is going from 0 to pi. So that's a distance of pi. Is that what we said the period should be at the beginning of the problem? Yeah, so that's good. That checks out. That makes me feel good that I've graphed this correctly. Now, I want you to be able to describe your transformation. Yesterday, when we were working with the A value being something other than 1, that was vertically stretching and compressing our graph. Okay, now we're looking at a B value other than 1. Okay, what happened to this black graph to make it this green one? What type of transformation took place? How would you describe that? Black is the original, green is the new. It compressed in what direction? Horizontally. Okay, so yesterday, A was vertical stretch and compressions. Now the B value is going to affect the graph horizontally because the B value is inside the function. It's part of what you're taking sine or cosine of. to get the common denominator? Yeah, I was just multiplying, I was creating everything, putting everything as a fourth to get a common denominator here. And that's to help me make sure that I can easily see that those values are evenly distributed. Okay, because when you go to plot your points, if there's like a pi fourth between the first 2 points and then all of a sudden like a pi half between the next two, that doesn't make sense. They should be evenly distributed, the same distance between each pair of points horizontally. Okay, so this is a horizontal compression. Okay, so this graph from the black to the green, it's like we put our hands on the left and right hand side of the graph and we squeezed it in. Okay, we compressed it horizontally. Remember, when you have values inside the function with x, they're affecting the graph horizontally. In this case, compressing horizontally. Okay, and you can see when we were doing our table, we divided by 2 to get x, right? So that's what happened to this graph. It is half. It is half. Divided by 2 is half. It is half the period of the parent function. It is compressed by 2. Does that make sense? And that's going to happen. A horizontal compression will happen anytime the absolute value of b is greater than 1. Okay, so anytime that coefficient in front of x is bigger than 1, that's going to be a horizontal compression. Some people get confused on that because yesterday when we did vertical compression, that happened when a was less than 1. It was compressed. And you would think that for a lot of people that makes more sense. You say when the number is smaller, it's compressing smaller. Okay, but if you think back to algebra 2, remember when you had numbers inside your function. So let's say you had +2 inside the function, that actually shifted the graph left 2. If you had -2, it actually shifted the graph right 2. Do y'all remember that a little bit? It was the opposite direction of that plus or minus when it was inside the function. The same thing applies to the compression or stretch horizontally when this is inside the function. It's the opposite of what you would think. So even though this number is larger than 1, it's not making the graph wider, it's making it narrower. Okay, it's compressing it. It's getting smaller. Does that make sense? Okay, so let's try example 5. What is your A? So the amplitude will be 1. Good. What is your B here? X is the variable. So X is not going to be part of the B value. The B is just a number. Nope, that's the trig function, just a number. If it was just 3, it would just say 3x. Because it's x over 3, the b is 1/3. There's an understood 1 here in front of the x. So this is 1 over 3 times x. Good. Does that make sense? B is 1/3. Okay, so the period then is 2 pi divided by b, or the absolute value of b, so 1/3. So we've got a fraction and a fraction again. What do? Multiply by the reciprocal of the denominator, right? So if I flip 1/3, what does it become? So what's 2 pi times 3? Good. So the period of this graph should come out to be 6 pi. The amplitude should come out to be 1. That's what we're going to check at the end when we finish graphing. Okay, so I'm going to start with my critical points column always, and next to that will be the trig column. Okay, what am I taking cosine of here? X over 3. Okay, so that's what's going to go here for the critical points column. This is x over 3. And the trig column is cosine of x over 3. Cosine is 1, 0, -1, 0, 1. And I don't need a column for the amplitude change because it's just 1. So these are the y values. Okay, these two columns, this is the parent function. I can go ahead and plot the parent function again. Okay, 0, 1, pi halves 0, pi -1, 3 pi halves 0, and 2 pi 1. You can see the scaling on this graph is by pi halves. Each little tick mark is a pi half, pi over 2. All right, now to get x alone, what am I going to have to do to get rid of that divided by 3? What's the opposite? Multiply by 3. Okay, so because it was a fraction, I'm actually multiplying to go backward instead of dividing. Okay, because remember, if I were to divide out, that's what we did up here, divide out the b, divide by 1/3 is actually the same as multiplying by 3. I'm multiplying this column by 3. I get 0, 3 pi halves, 3 pi, 9 pi halves, and 6 pi. If I want to get that common denominator to check the distribution of those, I would change all these to halves. So this would be 0 pi halves. This one's already 3 pi halves. Okay, the understood 1, to change it to a 2, I'd be multiplying by 2, so this would be 6 pi halves. This one's already 9 pi halves. And this would be 12 pi halves. So looking at, now that they're all in a denominator of 2, look at the numerator, 0, 3, 6, 9, 12. Is that evenly distributed? Is that the same value between each of those numbers? Yeah, it's plus 3 pi halves, plus 3 pi halves, plus 3 pi halves, plus 3 pi halves. So that's a good sign. So I'm going to plot my points now. I've got my x column. My y column is when I've got the entire function, which is just cosine of x over 3. I'm ready to plot those points. 0, 1. 3 pi halves 0. 3 pi -1. And if you're struggling to figure out where this is, if you've already checked that it's evenly distributed, look how many tick marks did I go between the first 2 points. And then I went 3. So the next point is going to be 3 tick marks over. And the next one is going to be 3 tick marks over. Okay, so I plotted those 5 points. I can sketch the curve. I'm going to verify my amplitude. That's 1. Is that what we said it would be at the beginning of the question? Okay, the period from the beginning of the cycle to the end of the cycle, from a high point to a high point, 0 to 6 pi, that's 6 pi radians. Is that what we said the period should be? Beginning? Yeah. So the amplitude and period check out to what we said they should be based on looking at the equation. So that's good. How would you describe this transformation? Horizontal stretch. And this is going to happen anytime your b value, I should say the absolute value of b, is less than 1. That's going to be a horizontal stretch. Okay, so similar to the compression, our hands are on the left and right hand side of the graph, and we stretch it horizontally. Okay, and again, you would think a value less than 1 would mean it's shrinking, but this is actually stretching it because it's inside the function, so it's the opposite. Are we good with that one? So A, vertical stretch and compression, and if it's negative, it reflects it over the x-axis. B, horizontal stretch or compression. Are we so far so good with what we've talked about in part 1? All right, one more vocab term for this section, frequency. You've probably heard that. Most of you have probably taken physics or you're in it right now. And you've done like sound waves, different types of waves. We talked about frequency. Say again. Harmonic motion, yeah. Okay, so frequency is of a sinusoidal function is how many cycles are completed in one unit. Okay, so if you start at 0 and you go to 1, you can see 1 right here. 0 to 1, how many cycles are completed? That's the frequency. So if we start here and we start this cycle, this is a sine cycle, right? That shape right there, that's sine. Y'all agree? So that's 1 cycle, and then it repeats, that's 2, and then it starts a third, but does it finish? Halfway, right? So there's 2.5 cycles, so that's the frequency, 2.5. Does that make sense? So that's how many cycles were completed when you got in one unit from 0 to 1, or it could be from 1 to 2, or from 2 to 3, just 1 unit interval. Now the frequency is all, because we're talking about the width, okay, it's related to the period. Okay, the period was how many degrees or radians were in one cycle. The frequency is the reciprocal of that. The frequency is 1 over the period. And since period is 2 pi divided by b, the frequency is b divided by 2 pi. The absolute value of b divided by 2 pi. Okay, so that's how you can determine frequency, or if you're given frequency, how you can determine b to write the equation. Okay, so just to give it some reference, let's think about frequency of that last example. Okay, what was the period here? 6 pi. What is pi? What's the number pi? 3.14. Okay, so here's 3.14. So would we say 1 unit? 1 is like over here-ish, about right here, right? Approximately, about a third of the way to pi, because pi is 3.14. Y'all agree with that? So if I wanted to know the frequency of this green graph right here, okay, it's just this little tiny piece right there. That's how much of the cycle is completed in 1 unit interval. So it's not even a full cycle. It's not even a quarter of a cycle. Okay, it's a real small number. Okay, and we could get the number because we know the period is 6 pi. The frequency is 1 divided by the period. So 1 divided by 6 pi is approximately 0.05. If you calculated it. What that means is this is about 5% of 1 cycle. It's about 5% of that green graph. Y'all follow that? So the frequency here of the green one is 0.05. It's very small. Y'all good? With understanding what frequency is measuring on the graph or in a function? All right, let's try this example here. A musical note, musical notes are classified by frequency. In an equal tempered scale, middle C has a frequency of 262 hertz. Use this information, and it says the information at left, it's the information above that we just talked about frequency, to write an equation for a sine function that can be used to model the initial behavior of the sound wave associated with middle C having an amplitude of 0.2. All right, so I know my goal here is to write a sine function. Okay, so y equals a sine of bx. Okay, There's no horizontal shifts or anything. This is what we're starting with. Now the information they give us the frequency and they give us the amplitude. Do either of those just directly get plugged into the equation? Which one? Where does it get plugged in? Okay, so the amplitude gets plugged in for A. So 0.2 is going to be the A value. Okay, what about the B value? Do I just plug in 262 there? No, B is not the frequency. What is frequency? How do I find frequency? What was that that equation up there? Or B over 2 pi. And I want to know B. Okay, so I'm going to use the absolute value of B over 2 pi. B over 2 pi. So I'm going to plug frequency in here for the F. So 262 equals B divided by 2 pi. How am I going to solve for B? Okay, get rid of the 2 pi by multiplying it over. I'm just going to leave this in terms of pi. I don't need it as a decimal. So what's that going to come out to? What's 2 times 262? It's 524. Pi is B. So that is going to get plugged in for B. So now I can write the equation as y equals 0.2 sine of 524 pi x. Does that make sense? Okay. Now, just think about it. This said the initial behavior of the sound wave, because what happens to a sound wave over time? Yeah, it dissipates. Like the sound doesn't keep going forever. Like if you like push the middle C on a piano, it's not just going to play that tone forever. Okay, it dissipates. But initially, that initial sound wave would be represented by this sine function. But then the amplitude would get smaller and smaller and smaller, right? All right. Last example for part 1. We're going to do one that has the A and a B value other than 1. So we've done a few of A alone and a few of B alone, and we're going to put it all together. Okay, so what is the A value here? The 2 or the 3? 2 is the A, and what does that tell me about the graph? So the A affects it vertically. Okay, so it's going to stretch vertically, good. But what measure does that tell me about the graph? What's that term that measures like how tall the graph is from the midline? Huh? Amplitude. Okay, so the knowing that A is 2 tells me that the amplitude will be 2, which y'all have told me that means it's vertically stretched by 2. Good. Okay, and then the B value is what? The 3. And what does that tell me? My period is what? It's not 3. B is not the period. B helps me find the period. 2 pi over B. Good. So 2 pi divided by 3. So 2 pi thirds. That's the period. So the amplitude should be 2. The period should be 2 pi thirds. You told me amplitude of 2 means a vertical stretch. What does a B of 3 mean if you're describing the transformation? It's horizontal, right? It's affecting the horizontal. Is it stretching or compressing when B is bigger than 1? Compressing. So this is going to be vertically stretched, horizontally compressed. Good. Okay, so let's plot these points, come up with our table, and see what it looks like. Okay, so we'll have the critical points and trig column to start. What should I put as the header or the title here for the critical point column? What am I taking cosine of? 3x. Okay, so 3x goes here. Okay, and then the trig column, so this is cosine, so it's going to be cosine of 3x. Cosine is 1, 0, -1, 0, 1. Okay, those two columns right there, those ordered pairs that you're looking at, just in those two columns, that's the parent function. I'll go ahead and plot it. Okay, pi halves is going to be right here between pi thirds and 2 pi thirds. And pi -1. All right, there is the parent function. Not the best curve I could have drawn, but that's okay. All right, this one has an amplitude, so there's going to be a column, and I say it has an amplitude other than 1. So there's going to be a column to the right of the trig column. So I'm going to do 2 times cosine of 3x. Okay, so to get those values, I have to multiply by the amplitude. We're multiplying by 2. 2, 0, -2, 0, 2. That's the entire function, right? 2 cosine of 3x. So that is my y column. So those are the y values. Okay, now to get x by itself, I have to go backward from the critical point column. How do I get rid of that 3? Okay, so I'm dividing by 3. Okay, so that's 0. That's a pi 6. Again, when you have a fraction divided by a whole number, you're actually multiplying the denominator by that number. So that's why pi halves becomes pi 6. Okay, and this becomes pi thirds. This becomes 3 pi 6. And this becomes 2 pi thirds. Okay, if you want to get the common denominator, it would be to make all of these in 6. Okay, that's already as a 1 pi 6. That'd be 2 pi 6. That's already 3 pi 6. And then this should be 4 pi 6. Is that evenly distributed? 0, 1, 2, 3, 4 pi? Yeah, those are spread out, evenly distributed. That's good. That's a good sign. So now I'm ready to plot those points. Green is the x value, purple is the y value. So there's a point at 0, 2. At pi 6, 0. So here's pi thirds. So pi 6 is halfway there. Pi thirds, -2. 3 pi 6, 0. And 2 pi thirds, 2. So there's that curve. So I'm going to label the amplitude and period on there and match it up with what we said at the beginning. So high to midline, or you could go low to midline. What is this amplitude on this graph that I drew? 2. Is that what we said it should be? That's good. Okay, the period, high point to high point. 0 to 2 pi thirds is 2 pi thirds. Is that what we said it should be? Yes, it is. So it looks like I've graphed it correctly. And I'm going to put the description you told me at the beginning without even knowing what the graph looked like. Just looking at those numbers, you told me the description of the transformation, but now you can see it. It is vertically stretched by 2. It's twice as tall. And it's horizontally compressed by 3. It's 1/3 of the width. Does that make sense? So this is a vertical stretch by 2 and a horizontal, horizontal compression by 3. We had to divide horizontally by 3. We had to multiply vertically by 2. So notice in your table, as you go to the right, you're affecting the y values vertically. Going to the left, you're affecting the x values horizontally. You'll feel okay about amplitude and period? Okay, there is a Delta Math assignment active already. I think I mentioned it yesterday. It's not technically assigned yet. You won't be able to do everything on there because part 2 of the notes is also included in that assignment, but you can start it. You can find the questions that ask about amplitude and period, and you can do some of those. Go ahead and get those knocked out. Okay?